Thank you so much. My name is Stefaan, and with me is Adrian today. Uh, as I was just introduced, we'll tell you about scraping leaky browsers today. Maybe let's, it's been a long day, it's been a very exciting day. Let's start with a temperature check, maybe. Are you guys all having fun at BruCON? Yeah? Yeah? Oh, me too. It's great. First time here. It's incredible. So, which of you people have like some experience with forensics and alike? So, investigating. Yeah. So I see a fairly high amount of people. I didn't expect anything less. So, people who have got a lot of experience with forensics, they'll be like, "Oh yeah, I know about this, but was it this bad though?" So, let's just. Oh, it's not working.
Yeah.
Okay. So let's go to the introduction. This is me. Um, I have studied computer science in the University of Leuven. I've specialized in security, and I did my master thesis on memory scraping web browsers. It was a team effort. Me and Viso we both made the thesis happen. I had a lot of help from them. Thanks so much. Currently, I'm employed by Planet Talent, so definitely check them out if your company is looking for juniors with high potential in IT and other industries.
Hi, so my name is Adrian. Actually, I have a bachelor in industrial informatics, and I have also a second bachelor in evening courses in security. And actually, I'm working as a .NET developer in consultancy in Belgium.
Okay, so let's get to it, right? A quick overview of what we're going to go through tonight is, well, we'll start off with what the hell is RAM scraping, right? And is it even a problem? What is the potential of a RAM scraper attacking me? What would it find? You'll see that RAM scrapers are indeed a big problem. And I have gone all out to test and find out how big of a problem it really is. After that, we'll look at the jackpot, the payload. Have a look at some countermeasures. We've also reported this to the vendors of the 3 largest browsers in the world currently, and they've responded to us, so it'll be exciting to get into that. And finally, we've written, Adrian has written, a volatility plugin that will allow you to consistently, effectively find sensitive data in the memory of browsers. And we'll give a demo too. So about RAM scraping, right? Where did this start? Where did this come from? This already existed many years ago in the world of academics. However, recently in 2013, I believe, a major American retail store called Target was attacked, and they had a bunch of records of credit card data stolen. 40-ish million people had their data stolen. And what happened is their point of sale systems, which are red because they're a target, were attacked by a memory scraper. Plain and simple, right? So these are devices that typically run embedded Windows XP probably. So, well, it's kind of, is it even like a problem on desktop computers, smartphones? Who knows, right? Probably not. I mean, this is ancient technology. We have operating systems that know what to do these days. Anyway, where did these RAM scrapers come from? Now, traditionally, especially since Snowden revelations have shown that your traffic while in transit isn't really secure, there's been a trend in IT security to encrypt all communication end-to-end. Not just important communication, also the communication of your WhatsApp, for example, is encrypted end-to-end. Now, what that means is, for example, let's take the example from Target again. If we have a credit card track data and we want to securely process it at our server, we'll have to find a way to transmit it through there. So we'll use the internet, but, we'll use encryption here. So before we send it over the internet, we'll encrypt our data. Nobody will be able to read it. It'll be perfectly safe. Now, as an attacker, you feel kind of grumpy seeing this. Like everyone's using HTTPS nowadays, even between the data centers of Google, there's HTTPS, so no matter where you are, you can like try to insert yourself on a wire or something, and it'll all look like gibberish. So very frustrating to deal with. So attackers have gotten pretty creative, and they said, you know, what if we move our vector? What if we attack before the data is encrypted? Or while the data is being processed? Because no matter how you look at it, credit card track data will have to go in a database at some point. What if we strike while the data is being processed? That would be, you know, genius. And it works surprisingly well. So to demonstrate to you that this is a giant problem, I found this interesting graph. I'm sure some of you are familiar with it. Here's a source right here if you're interested. Now, from all these huge data breaches, you can already see target here. I was off with a number. It's 70 million. Wow, it's even more than I remembered. Anywho, these are all the result of memory scraping attacks. You can see even recently there's been an attack, that's Wendy's, UPS Target, Staples, Neiman Marcus, a massive American business hack. So this indicates clearly that RAM scraping is a problem in the current world and the current landscape of computer science. So knowing and researching this, I set out and I decided to, you know, try out myself for a bit. You know, what are the possibilities? I'm gonna start a VM and I'm gonna look around, poke around, figure out how secure operating systems and browsers really are. So the first problem I encountered was, okay, how do you go from RAM memory to a username and password? There's a various amount of techniques. You can extract all the strings from memory. You can look for entropy if you're looking for cryptographic keys. But no matter which technique you use, you still need to acquire the dump of memory. It isn't very simple to acquire what's in the memory of another process, right? So I saw it like this. I said, okay, there's two ways I can get access to what's in here. We can either use a dump made in kernel mode, which means we have full access to the entire system and all of its hardware, and we can straight go this way. Now, what an attacker would do, or a malware, is, well, if they're doing this, you're kind of dead already. So what they would, the interesting angle at least, is to look at this. Use access via the operating system, look in the virtual memory, and then get it that way. So how you would do this is, you could use the Windows API function, open process, read process memory, and close process handle. I'm not making these functions up, they are real, and they work. They work very well. They work even as a limited writes user. You can open a process handle, read the process memory of another process of the same user if you're a limited writes user. If you're an administrator, different story, you have full access. And so that was one of the first findings. I said, wow, I can just dump any address I want with very low amount of restrictions. So creating the memory dump isn't really a problem for me, as long as I have an executable that's running on the target's machine. So then I had to decide, right? Because in the news there had been Target, and there were credit cards that were stolen. You know, I had a bunch of regular expressions ready to go after them. And I thought, no, what about something else? What about this case? We have Alice over here, and Alice has a lot of services she wants to use. She has her email, her mobile provider, her bank account, everything you want. Now, what happens nowadays if Alice wants to access any of these services is, well, typically, she'll go to one of her browsers, and the browsers will go to the services, and she will interact with them. So in order to authenticate herself as being Alice, because it needs to be obvious for the bank that Alice is Alice and not someone else, Alice can use, for example, a username and password. Why username and password? Well, it's free, it's simple, you can reuse it, it's very practical. I wouldn't recommend it, but it works. Now, you can see, like, if she uses the same password everywhere, we find a password in memory one time, or something that kind of looks like a password, maybe something she typoed, we would have access to all these services. Now, this already looks pretty chaotic to me. It gets even more chaotic because we also have mobile devices nowadays, and these contain passwords as well. So if I wrote a memory scraper that dumped the memory of browser processes and found usernames and passwords, that would be really interesting. That would make a good thesis, and it did. So the scope is the three most popular browsers, Internet Explorer, Edge, Google Chrome, and Firefox. And not only that, I also wanted to look at two different cases for each browser. Well, three actually. So the standard case where you launch your browser and you try to log in and then create a memory dump and see what's in there. You know, maybe the password and username are encrypted, so maybe there's nothing in there. Who knows? We can only look, right? So that's the standard cases. And now I was talking to this to, I think it was my sister or my mom, I'm not sure. But I was like, so what do you think? And they're like, oh, I'll just use in private mode. That's way more secure, isn't it? They won't remember anything about me then. And I said, well, that's a very naive thought. Like, that's not going to change anything. But I decided to test it anyways. You know, who knows, it makes a difference. And then, of course, there's another case where I said, what is the race condition on creating a dump? Do you need to create dump instantly after entering the password? Or do you have like some time frame you can play around with? So I came up with three basic cases in which a memory scraper would be effective in attacking a web browser. The first one is very simple. We have our user who tries to log in on this server. The browser encrypts the login data before sending it, you know, the whole SSL process. Sends it through to the internet, the server processes, data comes back. Now, where can the memory, this is the leading case of the three cases. So there are 3 points of attack for the memory scraper. The first one is right here. Before the browser encrypts the login data, it is in memory in plain text, because it has to be, right? How can you encrypt it otherwise? And so if a memory scraper is able to meet this race condition, it'll be able to retrieve the username and password as used. Now, second case, same thing, but we attack after the malware, after the browser has encrypted the password. So this would mean, this would be effective, if we're looking for plain text, it would be effective if the browser were leaky, for example. If it's allocating memory for its password before it encrypts it and doesn't free it. That would result in success. So that's another case. Finally, we have this case. Browsers have a very neat feature. That means you never have to remember any password ever again. You can just say, remember my password. So, of course, a memory scraper would also be successful if it found this password database. Now, you can encrypt it with a master password and so on and so on. But really, you're just moving the problem to one other key, one other string you have to find. So with these three cases in my mind, I went and investigated these three browsers, right? What I did was I created a clean virtual machine, and I launched Immunity Debugger and attached myself to each of the browser processes. I tried to log in, performed some actions a user would, and then I paused the process, and I went looking through the memory, looking for passwords I knew I had entered. And these are all vulnerable, of course. Otherwise, I wouldn't be here. So I was looking at the matches. Some of them were just plain text matches with zeros in front of them, but others, they had a pattern to them. So I decided this is something worth finding. I can write a program, run it in user mode, not in administrator mode. And I can just access the memory of any browser, and I will find passwords and usernames. So, time to go all out, full auto, write everything automatically, and get some test data. I want to know, how bad is it with these browsers? Maybe I just got lucky the one time I tried. Maybe it's a systematic problem. So in trying to automate this, I encountered these challenges. So I want to be able to dump my RAM as fast as possible. I don't want to wait 10 minutes. Otherwise, my use case of my timing attack, where how big is the window that I can find the password, would be kind of useless. So I also want to be able to run multiple tests in parallel, because, well, they're going to take a while if you want enough data to be statistically relevant. I want the results to be reproducible, so preferably just a script you can launch that then does everything else. And I want it to cover realistic situations. So I want the browser to be in a state that it would typically be in a desktop user environment. So I came up with this strategy here. The browser is right here. The browser depends on the operating system. I would need an input component to interact with the browser because I don't want to log myself into Facebook 20,000 times. That seems awfully tiresome and boring. So I'll automate that too. Then I need something that can create memory dumps, something that can parse it, something that can turn these parses into useful information, and I need something to make sure everything is running in the right order. And this is the implementation of that, is I used Windows 7 Professional on a virtual machine for parallelization, so I could run multiple at the same time. Here's me. These are the central component I was talking about. It turned out it was easier to turn them into two pieces. Here are our browsers. I used JUnit and Selenium to automate user interactions in a realistic way. Used procdump, because I told you, using the Windows API, it works. So I figure, why not just use a tool for system administration? Just use procdump. It's much faster than what I wrote anyway. I mean, I could spend time optimizing it, but as a malware writer, I could ship this to, no problem. And then, well, we have some scripts to parse the output. And so I found a jackpot. And how big is it? Well, before we can easily measure how vulnerable a browser is, we need to define a protection ratio. Now, what is a protection ratio? It's just a function that's one when a certain test case of a browser did not contain any passwords. So the higher the protection ratio, the better. So some quick examples, very simple. If I ran 100 tests and in 75 I didn't find any usernames or password, that means I would have a protection ratio of 75%. Similarly, here, 50,000 tests, elite cases without passwords, 63%. Now, the moment you've all been waiting for, the percentages, how vulnerable is each browser, which one is the best? Who says Chrome is the best? Can I see a show of hands? Who says Chrome is the strongest protected? Few people, yeah, okay. Who says Firefox? Okay, that's slightly more people. Who says Internet Explorer? Okay, there's a few insane people here. All right. Here are the results. Google Chrome is 33% safe against memory scraping, which is way more than Internet Explorer and Firefox. Oh, who would have thought? Internet Explorer is not last for once. Oh my God. Very excited. It's still not first though, and this is still absolutely horrible, right? This would mean that in over 60% of the cases, if you take a random browser state, I'd be able to find a username and password, at least one in there. It's crazy. Now, a little more detail. Remember what I was saying about the private mode and the delayed dump. So we can have, this is a lot of data. Let's go through it together. So for each browser, we have the default scenario, which is just you launching your browser. We have the private scenario, which is you doing the same thing in private mode. And we have a delayed dump, which is waiting 5 minutes before creating a memory dump that we're going to look through. So let's look at the standard results first. We can see Chrome as 13% protected against memory scraping out of the box. So you download it, you install it, you run it. 87% chance I will find usernames and passwords in your browser. For Internet Explorer, the number is 4%, and for Firefox, the number is 9%. That's abysmal. Now we can see in private mode why Google Chrome is so much better than the others. Because it's 61% protected against memory scraping when using it in private mode. So the naive solution of my sister or mom turned out to actually be right. That's crazy. That was also one of the things that blew my mind is, oh my God, private mode is actually good. You can see, except for Internet Explorer, it's, and Firefox as well, sorry. For the delayed dumps, you can see it's better for Internet Explorer and Firefox than in the standard scenario, and it's slightly better for Chrome. So what that means is there's probably some garbage collector thread running in the background, and after a few minutes, it starts to collect some sensitive data. Or maybe it's encrypting the data it's stored and gonna use it later somehow, who knows. some of these browsers are not open source, so we cannot verify. Okay, so how do we deal with this? How do we protect ourselves against this? Well, we can fire a missile at it, but that would leave our computer useless. So let's look into other options. So the problem is that usernames and passwords stay in the memory for far too long, right? I hope we can all agree. So how come? Possible causes and solutions. It's a bad implementation of malloc and free, which means I can call malloc and free, and the operating system will give me a chunk of memory, and it'll free it, or it won't free it, and it'll keep it for later use, in which case, you know, an attacker might be able to figure out what was in there before. So the solution that would be, instead of just, you know, freeing the memory and actually holding on to it and not zeroing it out, is zeroing it out. It's gonna have a slight performance hit, but I think it will be reasonable. Then we have bad browser code. This is the first one I thought of, but I don't want to, you know, kick all the browsers from a ledge, and you know, so bad browser code, code that allocates memory, never frees it. It's just there, remains there. Only solution to that is to audit the code. Happily, there are tools that will help you with that. For example, VeryFast is a tool developed at the University of Leuven, where you can annotate code and automatically verify that there aren't any memory leaks in your program. So that would help you automatically make sure that your code is secure that way. Then, you know, there's of course the possibility that Windows 7 does not quite manage memory the way we expected it to. So yeah, that's a tough break. How do we deal with that? We could stop using operating systems, but that seems like an awful idea. So, well, other than fixing the operating system, maybe we could look at protected module architectures. I don't know if any of you have recently bought a computer with a Skylake processor, for example. They have these cool new secure guard extensions on them. It's SGX. Anyone familiar with that? I'm not seeing too many people. Yeah, one person is. Okay, so that could potentially solve the problem. So what PMA is, wait, before I go on, I don't want to make this like a commercial for Intel. I also want to acknowledge that there's other variants out there developed at the University of Leuven and various other universities. Try looking into Sankus, for example. That seems pretty solid. Also has to do with Internet of Things for you attending the workshops there. So anyway, PMA is basically making it so that your memory runs in two modes, basically. Either you can, oh no wait, the memory is always encrypted, and there's only certain points at which you can enter and start running code. And every access to memory is checked and verified. So if one process were to try to read the memory of another process, the secure guard extensions or the PMA or the Sankus would prevent that, or even if they were able to read the memory anyways, it would come out as encrypted. So with SGX, there's still some work to be done. I understand that your software needs to be signed by Intel before you can use it, but this is in the future, definitely. So keep an eye out for that. Then there's, of course, the possibility that the browsers are exhibiting intended behavior, because every other month there's a new performance comparison. Which browser is the fastest? And they all want to be the fastest, even if it's just by a few milliseconds. So what if the browsers said, you know, we're not going to free memory we used. We're going to keep using it. Well, then, you know, we're kind of stuck. And yeah, the market is just this way. Of course, there's the possibility of single process architecture versus multi-process architecture. So what I mean by that is, I assumed before I started everything that Google Chrome would be invincible against this shit. I mean, it has so many processes that all eat so much memory, and then when you close a tab, it frees the memory, it's out of there, you don't see it anymore, it's gone. You're not supposed to be able to read it anymore. Turns out that, you know, if you play around with opening a tab, closing it, reopening it, closing it, reopening it, it only makes it worse. It explodes the amount of password occurrences in the memory. So I do believe that multi-process browsers should be more protected against this. Internet Explorer is multi-process too. Firefox isn't yet. I think we have to wait like 2 more months for that. Look into the E10 project if you're interested in that. Then, of course, there's the possibility that, when you enter a password, sometimes it asks you, would you like me to remember this password? And, you close it, or you're like, yeah, I remember it. Now, if you close it and it stays in the memory, that would be horrible. So a solution to that would be, we can just enter the username and password again if you want us to remember it, and then we can flush it out of the memory. It's gone. So now, the part you've all been waiting for, apart from the demo, of course, is the vendor response. What did the makers of the browser say to the developers? What did they say? First of all, here's Microsoft. It says, this is an issue. We acknowledge this. We're going to patch it in either October or November. And for those of you who have gone through Patch Tuesday this month, your browsers are now more protected against memory scraping, although not entirely. I ran some tests afterwards, and in a lot of cases it was better, but in some it was still, still vulnerable. But all in all, I could say this is a win. Thanks, Bill. Thanks, Microsoft. You did something right for once. Internet Explorer is going to be the next greatest browser, right? So Microsoft was also as pleased by our report that they made an official CVE. You can consult it on this page right here. It looks kind of like this. So all take note of this. I'm very proud of this. I'm very happy we realized this. And we were also officially credited. So they definitely acknowledge that memory scraping browsers is a problem, and they're trying to address it. They're trying to patch it. This is something we should encourage. Now, same thing with Google, right? We went to Google and we said, hey, look at this. Submitted a video of us dumping the memory, going through it. Look at how many password matches. This is absolutely horrible, even after closing tabs and visiting pages. And this is what they had to say. Sorry, this is not a vulnerability. This isn't the problem we have. This is something else. We can't do anything about this. Yeah, once you've added a malicious plugin, for example, it would be possible to get whatever information you want. But we're not talking about a plugin. No, we're talking about an external malware getting access to apparently a leaky browser. I would like to show them this graph and say, this isn't a problem. You have 33% protection against this. That's awful, in my opinion. So I would consider this a fail. There are also several duplicate tickets created that reported the same problem, and they all, let it go. They're like, not our problem. Well, Microsoft does agree it's a problem, so maybe they should look into it again. Then we have Firefox. They actually say the same thing. They say, if you have the capabilities of reading process memory, doesn't that mean, like, for example, a keylogger? I mean, we can't write our browser to protect you against keyloggers. Well, this is different. This isn't the keylogger. This is a process reading the memory of another process. It's not protected, and furthermore, why is the password still in there 5 minutes after I entered it, logged out, closed the tab, visited 10 other pages? It shouldn't be in there. I don't care what you say. So, also an epic fail. I'm kind of sad because I really like Firefox, but that's just me. I know most people use Chrome, so I'm fine with that. You all enjoy your 33% protection ratio. Meanwhile, I'll be, cruising through the land of Internet Explorer and Firefox. So I'm gonna hand the mic to Adrian, and he's gonna tell you about the plugin he wrote.
Thanks. So, my plugin is, I used Volatility Framework. And why? Because it's a GitHub plugin, a framework that is open source. Everyone can consult it. It's written on Python, which is quite faster. And it's multi-platform. We can run our plugin on Windows, on macOS, on Linux, which is quite interesting if you want to attack some browsers on different OS. Volatility Framework is one of the most used framework for extracting digital artifacts from RAM. And based on the advanced research of my colleague Stefaan, I get a target, which was a Windows 7 machine in 32 bytes version. As he told before, I identified some scenarios that I could try. So login on a tab, close it, or log in, log out, different scenarios to see how the browser reacts regarding the RAM memory. And for that, I don't mind how I get the way how I get the memories from the RAM. I just used Capture Live RAM from Microsoft, which is what was quite fast to script to get a dump from the memory. So my research was started at very low level. I get my dump, and I try to find my password that I set it for different websites, and as you can see, some patterns are detected. So in the URL post, we can see at email equals, at password equals, which much, oh, that sounds like a pattern that after that I can find some data, some interesting data. The next step was, okay, I have my data, I know that I have some passwords in my dump, how to do it? I investigate about some volatility plugins which were there, and I'd say, okay, that was a sample class that I have to define, and just trying to write it. Getting some parameters, getting some outputs, doing the job in the calculate definition. So I get a target, my Windows machine on 32 bits, how to implement my plugin. Let's say, as my colleague says, we get 3 browsers, Chrome, Firefox, and Internet Explorer as targets. And I try to investigate a few of well-known websites as Facebook, Twitter, LinkedIn, Instagram, Gmail, and some others. The logic of the plugin is quite simpler. You get for the volatility framework, I don't get only the process for a browser. I get entire dump of the memory. Okay, we are just limited to the size of the memory that we have to have enough free space on our disks, but I don't think that will be a problem at this time. So get my memory dump for each browser, for each process that you find based on my filters, which is filters website. Create my criteria based on the pattern that I defined before, and then try to analyze and parse every browser, every memory for the process that you find, filter it on your wish. Every pattern that you find, keep it away, keep it in a special array, and continue even if you don't get a password or not. Continue to the end. Once you get to the end, just show me what you have done, what you have found in that dump. So for the demo, I had just a dump of a memory. Let me just change the resolution on that. Well, it's not better. Yeah. Even worse. So I have a dump. On my machine, I get only 1 gigabytes of memory to be faster and say how it's going. And I have here the script to get the dump from the memory. It's a simple bet with a command, let's say, using RAM capture to have a dump. And also for my volatility plugin, I scripted in a bat file to execute, passing the volatility framework, passing my dump file. As I told you before, volatility plugin is multi-platform, so I have to specify a profile. That's my plugin names, and I want to filter on Internet Explorer and just show me what you get by the verbose parameter. By executing this script, we can see here in verbose, I don't know if you can see it very well. We can see it in verbose mode, what my plugin done. So he's searching for every process that he finds in the dump with IE explorer.exe, and then he parses in my criteria based on the patterns that I defined. So I can see for a dump with a size of 1 gigabyte, in 24 seconds, I get my user and my password here. Maybe I can try to make it green. Yeah, it's quite small. I don't know if it's better. So that was on my dump. I tried to log in on Facebook, a successful login, with my username, my password. As I know that it's for Facebook, that's based on my criteria, on array that I found, and he gets my credential find based on that scrapping of a dump. So that was quite fast to implement it and to run it. I know that actually Volatility, they have a program where you can subscribe for integration of our plugins that we are writing. It's not submitted yet, but because I would like to improve the plugin by a generic search. Generic search getting only a few patterns and try to mix it and find a lot of, I hope, a lot of credentials there. Later on this presentation, we will submit on GitHub our code. So for the guys who are interested in to have a look, to participate, to improve, remarks on other comments on that will be great to have your feedback. We continue with this.
Yeah, so, well, we did this before the patch of last Patch Tuesday, and I tried it after too, and well, to my surprise, there were still some usernames and password in the memory, not only in Windows 7, also in Windows 10. So even using the most recent version of the most recent operating system and the most recent browser, like, they're still vulnerable. It's gotten a lot better, don't get me wrong, but someone who's really persistent and really doesn't want to give up until they find what they need is gonna find it almost every time. So there are some other things, like actually just one thing I want to talk about, and that is LastPass. I don't know who is familiar with LastPass. I can see a lot of people nodding and raising their hands, yeah. Okay, so for those of you that didn't raise their hands, LastPass is a plugin for your browser that allows you to store passwords. And it does so using the cloud. So it's a very neat program that you can use to synchronize passwords across all your devices, use them anywhere you need to. And well, of course, it enlarges the exposure surface, because if I use a browser without LastPass and I use one with, like, it depends on how they handle their passwords. I would hope, you have to enter a master password to get to all your other passwords. And I would hope that unless I give that password and I give permission to LastPass to fill in my username and password automatically, it is not in the memory in a plain text way. I did find research on from someone just a couple of weeks ago who was like, hey, you know what? I'm going to look into the memory of browsers and their plugins. I'm going to look into the memory LastPass used. And he found the master password of LastPass, and he did find some plain text passwords also. And he did find them consistently. And if you're interested, I can give you a link, or I could show it on the screen later. So this indicates that, well, there's also been some other researchers who've taken notice of, you know, what about the memory of browsers? And it's good to see that more people are waking up to this, and that this is, especially if you're using a tool like LastPass, that's something you're supposed to be secure. They call it a vault even. It's supposed to be secure. It's vulnerable to such an attack is frankly sad. All right. Thank you for attending, and